Hello, my name is Carlos Souto and I'm a research fellow at the Faculty of Engineering of the University of Porto. I'm here to talk about fatigue behavior of cold roll-formed rail profiles for rack structures. This presentation was submitted to the first Virtual European Conference on Fracture. First, I would like to say that most of the presented work was conducted at the Faculty of Engineering of the University of Porto, known as FEUP. For those of you who don't know, the University of Porto is located in Porto, Portugal. It is one of the biggest universities in the country with more than 30,000 students. FEUP has around 8,000 students. You can see here in the pictures, on the right, we have the beautiful old city of Porto, and on the left, the FEUP's campus. Now, I would like to introduce the problem at hand. So, large companies resort to pallet carrying shuttles in order to deal with warehouse logistics. These shuttles are responsible for the transportation of various goods and products inside a warehouse. Now, these shuttles are usually automated so they can work non-stop. These shuttles run along thin, cold roll-formed steel rails. These rails are subjected to the cyclic loads due to the passage of a shuttle. These cyclic loads induce in the rail fatigue phenomena. Moreover, fatigue cracks have already been observed in these types of rails. The current situation is aggravated due to the competitiveness of the European industrial sector, which is pushing for thinner and thinner rails. All this leads to concerns about the fatigue performance of the rails. Obviously, in order to ensure safety inside a warehouse that contains a racking structure, design codes should include fatigue design curves for these types of structural elements, these thin, cold roll-formed elements. Currently, design codes, such as the Eurocode 3, do not cover the subject of thin, cold roll-formed elements, like the presented rails. Although design codes usually address thick, hot rolled sections, in these types of elements, residual stresses left over from their fabrication process are usually not relevant for the element's fatigue performance. What I just said is expected that it's not longer true for thin, cold roll-formed elements, where the residual stresses could play a significant role in the fatigue performance. Within the presented background, the Fast Cold European project has been carried out, whose research plan consists in developing fatigue design rules for the mentioned applications. At the Faculty of Engineering of the University of Porto, experimental fatigue testing has been carried out, backed by numerical simulations of these tests. A new fatigue testing setup has already been developed in order to generate representative fatigue cracking on the rail due to the shuttle's cyclic loads. Numerical simulations of the cold roll-forming fabrication process of these rails are also being carried out to determine the importance of the residual stresses in the rail's fatigue performance. Finally, the aim of this work is to present some of the work being done within the Fast Cold project. With the experimental data obtained from the fatigue testing backed by numerical simulations, important contributions can be made to design codes. So now I would like to show you the rail being tested at FEUP. So here on the top, we can see the rails section. It's called the Z profile. Here on the bottom, we can see the actual rail. And notice that the shuttle wheel can go along the rail's flange. So the wheel can go in these two directions here. So here on the top figure, on the right side, we can see at yellow, we can see a shuttle, and we can also see the rails. So now I'm going to talk about the development of a fatigue testing setup for these rails. So the experimental setup was developed throughout thoughtful trial and error, backed by numerical simulations. These simulations helped the developments of the testing setup. So here on the figures, we can see on the top here the real setup. We can see the two rails here, and we can see the load cell which can move up and down. Now this setup is capable of generating representative fatigue cracking in the rail. We can see here that the rails are clamped at both ends. And he also notes that this setup is capable of testing two rails at the same time. This is made possible because of the pin joint connection between the load cell and the load device. This pin connection allows the load to be evenly distributed to both rails. So fatigue testing is done through load control, while strain information is gathered with an extensometer. Now, obviously, the real-life loading scenario of the passage of a shell is impractical to replicate in a laboratory, so a seal load actuator is used instead. So as you can see here on the left side, we have our load actuator, our CAD design, and you can see that this load actuator is placed right here in the load cell. So it's actuating up and down the rail's flange. Now, as you can see here, this actuator is bolted on the load cell, so different actuators can be used instead. But we found out during testing that a smooth actuator with no sharp edges avoids local indentations and cracks on the web's flange. So an important aspect of our setup is that the load actuator can be placed on either side of the profile's flange. So here on the left, we have the actuator on the underside of the phalange going up and down. And here on the right, we have the actuator going up and down, but this time on the top of the profile's flange. So having these two possibilities gives us a better understanding of how can the residual stresses affect the fatigue performance of the rail. So now you can see a video of two rails being tested at the same time, with the load actuator being placed on top of the profile's flange. We call this a downward loading scenario. So in order to obtain the stresses at the profile's web to phalange corner, we are replicating our loading tests in numerical simulations. The strain information gathered from these tests will give us how many cycles the rail lasted. So we can see here on the bottom that this specimen actually lasted around 300,000 cycles. Now both loading scenarios, the upward loading scenario and the downward loading scenario, they both give us cracking on the profile's web to phalange corner. So this is expected because it is where we're going to find more concentration of stresses due to the section's geometry. So now I will share with you some of our fatigue test data obtained by the testing of this specific rail. So we have the geometry of the rail section with the dimensions, and the rail is composed of a S355 ms steel and has a length of 975 millimeters. So our fatigue tests have a loading ratio of R equals 0.1, so 10% of the maximum load. Now I shall clarify that in this table, the stress values here are calculated through a linear elastic finite element model that's replicating our load tests. Now this, as I said before, these maximum stresses are located in the profile's web to phalange corner due to the geometry of the section. The location of these max stresses are also where we saw fatigue cracking development. So if you want to take a look at this table, you can pause the video now. So finally, here's our first SN curve obtained by testing the Z rail. You can see in green the downward data for downward loading scenario, and at blue we can see the data obtained for the upward loading scenario. So remember, the downward, we have the actuator placed on top of the profile's flange, and the upward, we have the actuator placed on the bottom side of the profile's flange. So you can see here that the class 160 from Eurocode 3 for plain steel produces a very conservative fatigue life predictions for these rails. And we can also compare these two lines, and they have very similar results, despite the fact we were predicting some distinction due to the tensile and compressive residual stresses located in the cracks initiation sites. Now, one thing to note is that both of these lines have a slope of around 7 to 8, so the M value shown in error code 3. Now these are much higher than the base values of the design code. So finally, I would like to give a note on residual stresses. So numerical simulations are being conducted in order to obtain and analyze the Z-rail with internal residual stresses. These simulations are using both the real roll forming machine as well as the real elastoplastic material obtained through experimental data. So you can see here on the top, we have the definition of two paths. So the green path, first let me point out that at red here, we have the profile's web to phalange corner, and this is the crack initiation site. So the cracks appear right here. So this is where we are interested. Now we can see here at green, the path is going to pass through the outer surface of this corner, while the blue path is going to pass through the inner surface of the corner. So here on this graph below, we have the tangential stresses, the tangential residual stresses left over from the fabrication process. So you can see here at blue, the inner path, we have tensile stresses, while in green, at the outer path of the corner, we have compressive compressive stresses, residual stresses. So what does this mean? It means that when I load the profile through the top, like so, our downward loading scenario, we have tensile stresses on the profile's corner that are going to add up to the already existing tensile stresses, residual stresses. If, on the other hand, I load the profile through the bottom, the tensile stresses are going to add up with the compressive residual stresses left over. So this means that loading the profile from the top is actually a more aggressive scenario than loading it from the bottom. So during fatigue cycling, the mean stresses are influenced by the residual stresses. And during the downward loading scenario, the mean stresses will increase due to the tensile residual stresses at the inner surface. For the upward loading scenario, the mean stresses will be reduced due to the compressive residual stresses at the outer surface. This mean stress differences would impact greatly on fatigue damage. So in conclusion, this work presented a fatigue testing setup for real profiles. This setup allows for various configurations of load actuators, and it also allows for upward and downward loading scenarios. Within the Fast Code European project, this setup has already been used in order to generate SN curves for the real profiles. These SN curves, in conjunction with the work being done at the Fast Code project, provide important contribution to design codes, since these do not yet include considerations for thin, cold, roll-formed structural elements. These thin, cold-formed elements contain residual stresses left over from the fabrication process. These residual stresses can affect the fatigue performance of the rails. Although it is an ongoing investigation, simulations of the cold roll forming process are being carried out to determine the actual impact of the residual stresses in the structural elements and their fatigue performance. With that, I have concluded my presentation, and thank you all so much for your attention.